So continuing in section 6.2, we're going to still look at volumes of solids of revolution, but this time we're going to spin our regions around the y-axis rather than the x-axis. A lot of the ideas that we saw in the last video involving the disk method and the washer method will still apply. We just need to use them in a slightly different way here. For our first example, we're going to find the volume of the solid of revolution formed when the region bounded by y equals the square root of x, the y-axis, and the line y equals 3 is revolved around the y-axis. You might want to pause the video for a moment and copy that problem down. And the first thing that we should do, just like last time, is we should sketch our region so we see what exactly we're looking at here. So y equals the square root of x. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 0, 0, 1, 1, 4, 2, 9, 3, 6, 7, 8, 9. Yeah, that is correct. The line y equals 3 looks like this. So here's my region, and I want to spin this thing around the y-axis. We don't actually know how to do this yet, but I think you should be able to look at this region and decide, is this going to be a disk method problem or a washer method problem? Is there space between the region and the line I'm spinning around, or is there no space? And hopefully you'd say that there's no space. It's completely flush along that y-axis, so this is just going to end up being a disk method problem. Before we actually go to do that, though, I have 3 bullet points that I want you to get down in your notes. We're just going to call this a few notes. First of all, our representative rectangle, if we're using the disk method, or rectangles, if we're using the washer method, must always be perpendicular to the line you're revolving about, and we'll also have to start on the line and go to our curve. Your representative rectangle. Or again, if we're using washer method, rectangles, must always be perpendicular to the line you're revolving around. Your representative rectangle, or rectangles, must always be perpendicular to the line you're revolving around. So last time I was spinning around the x-axis. If I wanted something perpendicular to that, I need a vertical rectangle. In this case, when I'm revolving around the y-axis, something perpendicular to that would be a horizontal rectangle. The other piece, though, is and those rectangles must start on the line and go to your curve. Your representative rectangle, or rectangles, must always be perpendicular to the line you're revolving around, and they must start on the line and go to your curve. In this case, if we're going around the y-axis, my representative rectangle is going to start on that y-axis, and it's going to go over horizontally to my curve. One representative rectangle here because it's just a disk method problem. Next, if your representative rectangles are vertical, we are going to deal with functions of x and integrate over the x values just like we did last time. If the representative rectangles are vertical, we are going to deal with functions of x and we're going to integrate over our x values. That's what we spent the last video looking at. when we were spinning around the x-axis. We had vertical representative rectangles, we used functions of x, we integrated over x values. Our related version over here is going to be if the representative rectangles are horizontal, like I already drew in 1 for this particular case, we're going to deal with functions of y, and we're going to integrate over our y values. If the representative rectangles are horizontal, we are going to deal with functions of y, and we're going to integrate over y values. If the representative rectangles are horizontal, we're going to deal with functions of y, and then we're going to go and integrate over our y values. So again, going back to that problem, this is a disk method problem, so my formula is going to be v equals pi times the integral from a to b of just the radius squared, rather than the outer radius squared minus the inner radius squared, d, well, whatever that thing ends up being, d something. Our radius, the length of this rectangle, well, is just going to be this function over here, but instead of calling this y equals the square root of x, which is what it is, let me write that down somewhere. This is y equals the square root of x. My rule says when I'm dealing with these horizontal representative rectangles, I need functions of y, so I need to make this an x equals formula. Well, you can solve this thing for x by just turning it into x equals y squared. And I think that's going to give me my radius now. The length of this rectangle is just y squared. If you're over here, the length of the rectangle is 0 squared, 0. There is no rectangle. If you're over here at 1, the rectangle has a length of 1 squared. If you're over here at 2, the rectangle has a length of 2 squared, 4, and so on. Oops. My formula is going to be v equals pi times the integral. My radius is y squared, which I'll square, and I'm going to deal with this dy, because y is my variable here. The only other thing I have to figure out are my limits of integration. My rule also says I'm going to integrate over the y values. So the y values for this region go from 0 to 3, and this is going to be my problem. And I hope this looks a little similar to you as what we did when we were just doing the area between two curves when we were dealing with functions of y. We're integrating over y values. We have a function of y over here. At this point, go to the calculator. Type things in. Again, like last time, ignore the pi. Just type this thing in. You can type it in with an x. It doesn't really matter what you call your variable. But when you go to your calculator and do f and int on all of that stuff, you should get 243 pi over 5, I think. 243 pi over 5. Horizontal rectangles, we need functions of y. So if I have a function of x, I'm just going to solve that thing for x to get a function of y. And I'm going to go and integrate over my y values. I have 2 more examples that I need to show you. Not going to bother writing out the whole setup for this one. Our deal is we're taking a region, we're spinning it around the y-axis. My region is going to be bound by x equals y squared, y equals x minus 2, and I'm going to spin this thing about the y-axis. Looking at the region bound by the sideways parabola, x equals y squared, the line y equals x minus 2, and I'm going to spin this about the y-axis. And we need to start this by doing some plotting, and I will do this by hand. And I think I'm going to start with x equals y squared. You don't have to write out a table of values. You can just sort of think about what this is going to be, but I think it might actually help here if we see some of these things. I'm going to plug in 0 for my y. 0 squared is 0. I'm going to get out 0 for my x, so my first point is 0, 0. Plug in 1 for your y. Get out 1 squared, or 1 for your x, so 1, 1 is my next point. Plug in 2 for your y. Get out 2 squared, which is 4 for the x. Remember, this is not the point 2, comma 4. This is the point 4, comma 2. 1, 2, 3, 4, comma 1, 2. Let me deal with some negatives. Negative 1 squared gives you 1. This is the point 1, comma negative 1. Plug in negative 2, you get 4, so I have the point 4, comma negative 2. I'm going to see if this is good enough. If not, I'll add in a couple more points, but I kind of think this is going to work. Y equals x minus 2. Well, that's not bad. It's already in a good form for us. I'm going to start at negative 2. Slope is 1, so up 1 over 1, up 1 over 1, up 1 over 1, up 1 over 1. That worked out nicely. This is my region. And I'm going to go and I'm going to spin that thing around the y-axis. Is this region completely flush with the y-axis? No, so I need to use the washer method here. I'm going to need 2 representative rectangles and 2 radii. Both representative rectangles are going to start on your y-axis. The outer rectangle is going to go to the furthest away part of your region. So choosing between the parabola and the line is further away. That's going to be my outer radius. And my inner radius is going to go from the y-axis to the parabola, like that. My formula is v equals pi times the integral from a to b of the outer radius squared minus the inner radius squared. And horizontal things, I'm dealing with this thing, dy. Next, the outer radius is from the y-axis to the line. However, that line, y equals x minus 2, not okay to call it that. Because my rectangle's horizontal, I need a function of y. So I'm going to solve this thing for x. I'm going to get y equals x plus 2, and that's what I'm going to call this line over here, x equals y plus 2. It's the same thing as y equals x minus 2, but if I write it like this, it's a function of y, which is what I need here. Pi times the integral. My outer radius is y plus 2 squared. My inner radius, well, I'm going to the parabola. My parabola was already called x equals y squared. It's already a function of y, so I can just take that as it is, and I'm going to say y squared squared. This is dy. I'm looking at the y values that I see over here. I think my lowest y is negative 1, 0, 1, 2. My highest y value is 2, so I'm going to integrate this thing from negative 1 to 2. Again, go to your calculator. You can use x when you type it in, doesn't matter what you call it. Leave the pi till the end. And when you go to the calculator, you're going to get 72 pi over 5. One more example. I would like to deal with the region bound by y equals x minus 1 cubed and y equals 3x minus 1. And we're going to spin this about the y-axis. You should probably be able to plot that by hand, but whatever. If you just go to the calculator, that's fine. Get a sketch of the region and see what you can do. Maybe pause the video, see what you can do on your own, then start it up again when you're ready to take a look at some of my work. And let's see what we can do with this. So I've got the point 0, 1. I know this is a cubic function that was moved to the right one space. Got the point 2, 1. I've got the point 3, 8. 1, 2, 3, 4, 5, 6, 7, 8. Okay. Then over here, negative 1, negative 1, negative 2. I'm just going to kind of stop with that. Wait, hold on. No, that's not right. Sorry, 0, negative 1. And then I'm just going to sort of stop with that. I've got my cubic function going like that, and coming down like that. Y equals 3x minus 1, so negative 1's over there, up 1, 2, 3 over 1, up 1, 2, 3 over 1, up 1, 2, 3 over 1. I'm going to use my ruler. I've got this region over here. and I want to go and I want to spin that around the y-axis. There's space between the region and the thing I'm spinning it around, so it's going to be a washer method problem. Outer radius is going to start on the y-axis, go to the cubic function. Inner radius is going to start on the y-axis, go to the line. Again, I'd suggest you pause the video and see if you can come up with the setup, but maybe before you go to the calculator to evaluate, check my work and see if you're getting the same things as me. Outer radius goes to the cubic function, but you can't use it the way it's written. You can't say y equals x minus 1 cubed. You've got to solve that thing for x. You need a function of y rather than a function of x. I'm going to say cube root of y equals x minus 1. So x is going to equal cube root of y plus 1. Inner radius goes to the line, but again, you can't call it y equals 3x minus 1. We need to solve that thing for x to get a function of y. I'm just going to say x equals y plus 1 over 3. That'll work. So we've got v equals pi times the integral. Outer radius went to the cubic function, so cube root of y plus 1 squared, minus inner radius went to the line, so y plus 1 over 3, which I'll square, dy. I'm integrating, I'm integrating over the y value, so not 0 to 3, rather I'm going from negative 1 to 8, and that's what your setup should look like. You can find the cube root function under the math menu on the calculator, or forget about it and just call this thing y to the 1/3. That will work as well. Go to the calculator. I think you're going to get a horrible decimal like 24.3000000534 or something vaguely like that. This is just because the calculator has some difficulty integrating cube roots and really any sort of root and stuff like this. It is trying to tell you 24.3 on the calculator. Don't forget, though, we haven't dealt with the pi, so I'm going to stick the pi at the end. You can say 24.3 pi. You can say 243 pi over 10. You can forget about the whole thing and just give an overall decimal. As long as it's accurate to 3 places, that'll work. So this is spinning around the y-axis. The biggest thing you need to remember is when we're going about the y-axis, our representative rectangles are horizontal, and we need to be dealing with functions of y. Usually they won't be given to you as functions of y, and you'll have to just go through some algebra to turn them into x equals formulas. The last part of this solids of revolution bit, which we'll deal with in the next video, will involve spinning regions around other sorts of vertical lines and horizontal lines. It's still going to use similar ideas, we just have one extra little piece we'll need to add into that.